Okay, so as Bruce mentioned this morning, this talk is what we internally refer to as the scare talk, because we just showed you all this nice, fully automated stuff, and now we're raising the specter that some of the things could actually fail. And so there are certain things that you have to check on and ways to actually fix it if they are failing. So failure modes, troubleshooting. So you can have hard failures and soft failures, and we'll go through what those are. And basically, the type of failures that you can have come in several flavors. There's skull stripping errors, there's segmentation errors, intensity normalization errors, peel surface misplacement, and topological defects. And so I should preface this by saying that probably like 90% or so, if you have good quality data, it's often the case that you don't need to do anything to it. But you always should go through and check it because it's hard to tell. You don't know just because recon all finished whether it did the right thing or not. So hard failure is when you run recon all and it doesn't run all the way to the end. And a soft failure means that recon all finishes, but there's something that it didn't do quite right. So recon all has a lot of optimization procedures, and one thing about optimization procedures, it'll give you the best that it thinks that it is, but it might not be the right answer. Another indication that something is going wrong is that FreeSurfer takes even much longer than what we usually think of as long. So it's more than 20 hours. Usually what happens is that the cerebellum has not been removed, so it's trying to build a surface. You remember the different stages in FreeSurfer are that you go through and have a bias correction, intensity normalization, there's skull stripping, there is and white matter extraction. And then it takes the white matter and dips it into that chocolate member, and you end up with the ridge surface. That dipping into the chocolate where it's actually building a surface around the white matter will take forever if the white matter also includes, say, brainstem or cerebellum. So hard failure. If you remember from the previous talk that I gave, when you finish recon all, you have a folder which is your subject's name, and it has these 5 folders in it: scripts, URI, cert, label, stats, and under scripts it has this recon all.log file. And when you run it, it's going to print out something nice at the end that says, FreeSurfer finished without error, and then all you know at that point is that there's not been a hard failure. So if there's a hard failure, it's going to create this log file again. It'll also create a file called recon_all.error, and it will end by saying something like, FreeSurfer generated some kind of error, and it might or might not be obvious to you what that error is. It could be that you ran out of disk space, or that you didn't have permission to write to a particular file. It could be a pathological condition in the brain that FreeSurfer wasn't expecting. The thing that is about hard failures is that we don't program it to have a hard failure, and so when it fails, when it doesn't run all the way to completion, you have a hard failure. We don't necessarily know what it is, and so if you just write us and say, "Oh, FreeSurfer didn't finish. What went wrong?" We aren't going to know. So what you have to do is to send us this log file and say, this is what I was doing. This is what broke, and can you tell me what went wrong? The bigger problems, of course, soft failures. So, which means that basically the recon all finishes, but the surfaces are not accurate. I have here that it's not possible to directly edit the location of the surface. That was in the olden days before we were using Preview. With Preview, it actually is possible to adjust where the surface is. But most of the time what you're going to be doing is when the surfaces are inaccurate, you have to manually change the information inside of a volume and then regenerate the surface. So if you remember, there are basically three steps. There's intensity normalization, skull stripping, and white matter segmentation. And it's usually going to be one or a combination of those three things that are going to fail. And so all three of those are in the volume-based stream, so you're going to be editing and changing volumes and not changing surfaces themselves. So there are 4 manual interventions that you can make. You can erase a voxel. You can fill in a voxel. You can clone a voxel, which means to copy a voxel from one to another, from one volume to another volume. And you can add something called a control point. And then after you make these manual changes, then you would rerun parts of recon all, so you don't have to go in and rerun everything from scratch. So it should only take a couple of hours after you make an edit to a volume to rerun the remaining part of recon all. And it's also possible to change parameters in recon all, but that's a little bit more advanced. And just as a reassurance, this is the reason why we call this the scare talk, because basically you're going to be looking through this volume and looking at where all these surfaces go and whether the surface is accurate or not. And it's not going to be entirely clear whether it's accurate or not. And so you have to get some comfort level, and generally people start in a position of feeling very uncomfortable while they're doing this. So just to give you some reassurance, most of the time when we're doing these types of edits, it takes like a well-trained person maybe 30 minutes to go through the brain, make some changes to the brain, and then just relaunch FreeSurfer. And so, it can be a little bit overwhelming as you start looking at these brains and looking at the surfaces and think this will take me forever. And in reality, 30 minutes is oftentimes an overestimate. So most of the time, probably it takes 15 minutes or so. So that's a little bit more reasonable. So I want to throw that out there to give you a sense of there are boundaries and limits on this. And most of the time, if you don't know, if you can't quite decide whether the surface is accurate or not, leave it alone. In general, you don't want to edit too much. Most of the time, FreeSurfer is going to do the right thing. And if you get in there and start messing with it, then you might actually break something. Okay, so as I said before, these manual edits are applied to volumes and not to surfaces. And so I have this little matrix here of volumes that you apply changes to, and these 4 edits that you can make. Remember, you can erase things, you can fill things in, you can clone, or you can add control points. And so depending upon what you do, your next the next thing that you run may be different depending upon which change that you make. So actually, I'll just go through some of these. So this is just the workflow in stages. So if you add control points, you can run recon all, but instead of giving it a dash all, which tells it to do everything, you give it dash auto recon to dash CP. So that tells it to start where control points are and do everything after that. If you want to look at all the gory details of what's happening in the stream, you can point your web browser to this location, and this goes through like each individual step that recon all is running through. Okay, so there are basically 4 manual interventions that you can make. You can erase voxels, you can fill in voxels, you can clone voxels, and you can add control points. So this is a situation where you have a skull strip failure, and that the skull stripping has removed too much, taken a big bite out of cerebellum there. And so what you have to do is to go in and, so it's removed too much, and so what you have to do is copy voxels from the unskull stripped image back into the skull stripped image. And so that's the cloning tool. You can have a skull strip failure where it hasn't removed enough. So here's a situation where the eyeballs, part of the eyeball was left inside of the brain, and Recon all saw that there was a bright transition there and happily said, okay, that must be white matter, and so I'm going to build a surface around it. And so the fix for this would be to go in and erase. So we've got cloning on the previous page, and we've got erasing on this page, where you just go in and erase those eyeball voxels and basically manually fix the skull strip. Another place where you have a problem is here near pars puppillaris, pars triangularis, where you have this little bright area there, and this is either dura or a blood vessel or something like that. It's shown up very bright, right on the edge of cortex. And again, FreeSurfer saw that, so that's a nice bright to dark transition. That must be the edge of a surface. And it went in and it pushed the peel surface out to include that vessel or whatever that is. So the fix for that would be to go in and erase that vessel, and then FreeSurfer would then only send the surface out to where the edge of the true peel surface is. So I think somebody asked about this earlier. So this is a case where there's a lot of, I guess, PIA that's there that was left by the skull strip. So this was the original image, and then this was the skull stripped image. You see there's a lot of PIA that is there, and this is the outer covering, or sorry, dura that's there. This is the outer covering of the brain. And so a lot of people would look at this and say, oh, that was a skull strip failure. But if you look at the surfaces look totally fine. So yeah, the skull strip could have done a little bit better, but in reality, the surfaces are totally fine. And so in that case, there's not really any need to go in and erase those voxels from the skull strip because they're not really affecting anything. So that was the first class of error, which are the skull strip errors. And so the skull strip can either, yeah, go ahead.
What's the advantage of editing just a small portion, either cloning or taking away voxels, as opposed to just simply going in and adjusting threshold?
So what's the advantage of removing or adding voxels relative to just changing the threshold? So the threshold that he's talking about is an input to Recon all, that you can actually go in and say change the minimum threshold, change the maximum threshold. And in that way, you can also alter the how much the skull stripping will remove. So if it's removing too much, you could go in and say lower a threshold or so. In that case, the rule of thumb is that if you're having to do the same thing over and over again, then it's probably some quirk of your acquisition that is causing like too much to be removed or not enough to be removed. And in that case, you would probably want to make a global change and just change it for everybody. However, most of the time, FreeSurfer does a pretty good job, and then there'll be like a few subjects that will have these skull strip errors. And in that case, probably you would just want to use the default parameters inside of FreeSurfer. Because otherwise, these are the parameters that everybody is using, so they have a lot. They have a lot of mileage on them, and so you can have more confidence, I think, rather than going and changing your own thresholds. But if you're constantly seeing some error, then it might be better to change the threshold for a group of subjects. So that was the first type of error. It was the skull strip. So the skull strip is either going to remove too much or it's not going to remove enough. And if it removes too much, then you clone. If it doesn't remove enough, then you erase. So the second class of errors are the segmentation errors. And they have two types. White matter is classified as non-white matter, or gray matter is classified as white matter. It's basically an error in the white matter segmentation. So in the first case, you have a situation where you have white matter that's actually being classified as non-white matter. So this is an older subject who has a white matter lesion, which is right here. And if you kind of look at that, white matter lesion basically looks like gray matter. And so it said, okay, that's gray matter, that's great. I'm going to draw a surface around it. And so what you have to do is to go into the WM.mgz, and in that spot there will be a hole. And so you have to go in and fill in that hole. Do you remember when I was drawing the bunny ears, and I drew the bunny ears as white? So basically you turn on the bunny ear application in 3D, and you go to that spot and you put a little white dot on there saying, no, this is really white matter. So that's the first type of segmentation error, is that white matter is classified as non-white. And so you end up with a hole, and FreeSurfer generates a surface around the hole. Is this a segmentation error? Looks pretty similar to what was on the previous page, right? But if you look at this in 3 dimensions, what's happening is that, so this is what we saw before. What's happening is that this particular coronal slice is just cutting off just the very end of this little gyrus here. And so if you look at it in the sagittal view, you can see that the surfaces look totally fine there. In the axial view, they also look totally fine. So if you think of it as like that little gyrus as being like a little piece of bread, if you just cut off the very end of that piece of bread, that's what you're seeing here. And so it looks a little bit funny. So this is a good thing to know, is that when you're looking at these things and you're judging whether the surface is accurate or not, and you think that you found a place where the surface is not, look at it in all of the other views, because sometimes one view will look really, really funny and the other views look totally reasonable. So also on the segmentation error, which I don't think I have an example of here, you can have a situation where white matter is classified, or gray matter is classified as white matter. And so then what it does is it builds the surface through that particular piece of gray matter. And you'll work with one of those situations in your tutorial. You might have one later on. So 2 classes of errors so far. Brain masking errors, where you have too much is removed or not enough. You have white matter segmentation errors, where white matter is segmented as non-white matter, or non-white matter is segmented as white matter. And so the third class is this intensity bias error. So this is the same slide that I showed on the previous talk. Oh, sorry.
Just before we move on, sometimes you have in older subjects white matter hyperintensities. So you can't just go and make those white because they are not white. I mean, it's white matter, but it's denigrated. So what do you have a recommendation in that case?
So the question has to do with when you're dealing with older subjects who have white matter lesions. And so what it appears that I'm suggesting is that you go and redeclare those lesions to be white matter. But this is not actually what's happening. This is the WM.mgz, which is not, as I mentioned in the first talk, the WM.mgz, this is this white matter segmentation, is somewhat misnamed. So it's supposed to be everything that's inside of the cortical surface. And so that's what we're calling the white matter segmentation here. So in this case, all we're doing when we edit the WM.mgz is saying, this should be inside of the cortical surface and not outside of it, essentially. So intensity bias, if you remember from this morning, this is these slow fluctuations across space of intensity. So in this case, the right side of the image is much darker than the left side of the image. And in fact, the white matter on the right side of the image is as dark as the gray matter on the left side of the image. The human eye is horrible at being able to pick these things out. It's actually the visual system is set up to remove these types of things. So it's very difficult for you to look at these things and see that there's an intensity gradient. And so when this happens, this causes all kinds of problems, because if you're trying to do segmentation, if you're saying that white matter is, at this level, and everything at that level and below is white matter, declared to be white matter, and everything above that level is going to be gray matter, then this is going to cause a huge problem in your ability to segment. So we implemented this intensity bias scheme where it tries to estimate what the shadow is that's being cast across the MRI image, and estimate that and then remove it. And most of the time this works pretty well. So in this case, if you look inside of the T1 image in white matter, most of it is going to be 110. So if you brought up the T1.mgz in Freeview and you clicked on a point in white matter and you looked down at what the voxel intensity was, you would see that it would be about 110 for most areas in white matter. And so if it's not, then that could indicate a problem. And the fix for this, so internally what FreeSurfer is doing is that it's finding areas that it thinks with a very high probability are white matter. And it says, okay, I'm expecting white matter to have the same intensity across the entire image. And if it's not, then this must be the shadow that's being cast across the image. And so it estimates from these white matter points what that shadow is, and it tries to remove that shadow. But the thing is that it has to find points that are very confident are actually white matter in order to be able to do this calculation. So it's a little bit conservative. And so what can happen is someplace like here in the temporal lobes is often a case where you have these shadows. And it's also a case where you have very thin white matter, areas of white matter. And so what you can see here, is that there are some of these gyri there that are being cut off here. So the white matter surface should actually go in and like fingers like pushing out of that gyrus. And so the fix for this is to put in something that are control points, which you can see here are these green plus signs. And so what that does is that tells the FreeSurfer intensity normalization, these are definitely white matter. So you can use these to remove the bias, to remove this shadow that's being cast over it. So two important things. If it's already 110, then it's not going to have any change whatsoever on FreeSurfer. The second thing is that you have to put them in areas that you know are 100% white matter. So no partial voluming, definitely no gray matter, definitely no CSI. So places that you are very confident are actually white matter. And then you can go in and put in a couple of control points around there, and then you would rerun parts of recon all, and it redoes the intensity normalization with the knowledge that those points are white matter. And so those control points will then end up affecting an area around them. And so in this way, you have this slightly non-local effect, that you have a problem that's out here, but you put the control points further into the white matter, and it ends up having this non-local effect. So I think I said this, use them relatively sparingly. Sometimes we get emails on FreeSurfer list, somebody put in like 1,000 control points. Usually that means that something went wrong somewhere along the way. They're not necessarily associated with a particular volume. So whereas with skull stripping failures, you would edit the brain mask. With white matter segmentation errors, you edit the WM.mgc. Control points are just points in space. So you might apply them while you're looking at the T1, but they're not associated with any particular volume. And they're saved as just a separate text file inside of the subject stir. Another point are something called topological defects. And so these are relatively complicated things that you can see here. So in one case, you have a little bridge across a gyrus. So in this case, white matter or gray matter in the middle of the sulcus was labeled as white matter, and it just built a surface around that. And so where you have a hole here is where white matter was labeled as gray matter. So maybe there was like a little lesion there or some scanner artifact, and it just turned out to be darker, and it was labeled as gray matter. And so it said, okay, that must be inside of the white matter surface, and so it's going to build this surface around it. The problem with these two things is that they're topological defects, meaning that if you were to take this and inflate it, it would not have a spherical topology. So the good news is that these things are automatically fixed by FreeSurfer. There's an automatic topology correction inside of FreeSurfer, and it usually works really, really well, but it doesn't always work perfectly. So the way that it works internally is it says, it looks at these things and says, okay, that looks like a bridge from one sulcus to another. I'm going to cut that out. And even though this was originally segmented as white matter, this little bridge, I'm going to resegment it as non-white matter. So this indicates a segmentation error. And then this one, it would say, okay, that looks like a hole. So I think I'm going to take that and fill it in and say, the stuff that was non-white matter, I'm going to say is now white matter. And so that's what it does, and that's how it works. And it usually does a pretty good job, but it will occasionally fail. And sometimes you'll be looking through your slices, and you'll find areas where the segmentation doesn't quite look right. So this is just a segmentation error. It's not a new class of error. It's just a type of segmentation error that automatically gets fixed, but sometimes it doesn't automatically fix it correctly. And these are just typical places where you might see topological defects. So this is not an error. So this is what I brought up earlier, which is that each hemisphere is analyzed separately, and each hemisphere is its own closed surface. And each hemisphere is not in the brain. You don't have a whole hemisphere of cortical brain matter. You have parts of the hemisphere where corpus callosum goes through, and we have amygdala and hippocampus, for example, which are gray matter structures, but they're not cortical gray matter structures. And as such, FreeSurfer does not try to create an accurate surface through those structures. And so when you look at this, these things just look like they're kind of wrong. So these are the midline structures. But because they're on the midline and they are subcortical structures, it doesn't matter what path the surface traces through them. Some other things that are not errors. So here's a case where the volume, the color in the volume is the automatic volume segmentation. So we have pallidum and putamen and caudate and ventricles, and there's amygdala that's down here, and we have white matter, and we also have cortical gray matter. And if you look up here, you see that the cortical gray matter label does not match with where the surface goes through. So the question is this an error? So technically, it's an error in the automatic volume segmentation, but we never use the cortical information from the automatic volume segmentation. So the fact that the two don't agree is irrelevant. So this would not be classified as an error. So when you see this, you wouldn't necessarily need to go in and fix it, although it is theoretically possible. The most important thing is, do the surfaces follow the intensity gradients? So you look at the white surface. Is the white surface following the gray-white boundary properly? Is the peel surface following the outside boundary of the grain properly? Those are really the only criteria, and not whether this whether the subcortical or the volume-based segmentation agrees with the surface-based segmentation, because we know that it won't in cases. FreeSurfer remembers. So when you make manual edits, it will save those in the FreeSurfer directory. And if you were to say rerun with a new version, the FreeSurfer would preserve these changes. So this is nice because occasionally you want to just reanalyze all of your data, and this is a little bit tedious to go through all of your subjects, and you want to make sure that that your edits are preserved. So unless you tell FreeSurfer to delete an edit, it will keep an edit there the whole time. So to summarize, you have hard failures where FreeSurfer itself does not run all the way through, so recon all does not run all the way through. It crashes for reasons of disk space or permissions or something else that went wrong. More likely, what you'll have are soft errors. So hard errors are very, very, very infrequent, less than 1%, I would say. Soft errors are places where the surface itself does not follow the intensity gradient the way that you would expect. So you would look at the surface and you would ask yourself, would I draw this surface there? You change volumes and then regenerate surfaces. You generally don't operate on surfaces directly. There are 4 ways you can make manual edits. You can erase voxels, you can fill voxels in, you can clone or copy voxels, and you can add control points to fix intensity normalization failures. So there are basically 3 different types of failures. There's the skull strip, where it removes too much or doesn't remove enough. You have white matter classification errors, which are white matter classified as non-white matter, or non-white matter classified as white matter. And then you have intensity normalization failures as well. And make sure to look at all 3 views when you're looking at these surfaces and trying to judge whether they're accurate or not. Look at all 3 of the views before you make a final decision, and certainly before you start taking corrective action. And again, this should take less than 30 minutes per subject. Oftentimes for us, less than 15 minutes. And if you don't know, just leave it alone, and it'll be fine. Let's see.
Break, and then Allison does again, and then we got to.
Okay, so we have a break now. And if you have any questions right now, I can take questions. We have a break. There's probably more coffee out there. Then Allison will give a demo of actually going through and doing a quality check on the recon, and then you'll start doing your tutorials. Sorry, can you speak up?
The version that you just gave this is not what you downloaded online, unless I did something wrong. Is there another version of this?
Yeah, so the version that was online
sorry,
is
yeah,
the version
yeah.
that I usually give, which Doug evidently doesn't like. So we'll get the version that Doug gave online. So the version that Doug gave is the version in the book, I think.
Yeah,
Which is
so
why-
this was the version in the book, right?
Which was not so easy for us to change. So
Yeah,
that's
it's easier
all.
to change what's online. And so I can do that. We literally just discovered that like seconds before the talk. So I apologize for that. And by this afternoon I can have a switch.
I'm just curious, if we went in and made some manual edits and then just did a recon all, would that redo every single thing, then take the edits into account when it got to the appropriate place in the stream?
So the question is, if you made manual edits and you ran recon all with a -all flag, so it would go through and it would redo everything, and it would include the edits that you have stored in there. You can also do a recon all -make and then all, and it will start the stream in the right place. It'll see, oh, you edited the w.mgz, so I need to start here, and it'll run everything forward.
For the bridges and the holes, is this something that guess that you could go very carefully through the mesh view and make sure that you don't identify them, but otherwise it's something that would be evident either in your reconstruction where there's a mistake where you think, well, this is likely to be a bridge wire hole, so I should go back to this anatomical, size and specifically figure that out.
So the question is about bridges and holes, and Recon All will fix all of the bridges and holes, so you will not see a bridge or a hole in the final surfaces. So the question is not whether you would see them or not. The question is whether Recon All fixed them properly or not. And so it's not part of the tutorial, but you can actually bring up an image with all the topological defects that that Recon All found and fixed. And so you can look at each one of those and see whether it did the right thing or not.
The way to tell that there was a topological defect is if the surface doesn't follow the WM.MGZ. So the ridge surface should follow the surface of the stuff that's non-zero in the WM.MGZ, except where a topological defect was corrected.
Okay, great.